So now that we've looked at solving systems of equations in their linear equation format, we need to establish an easier way to solve the systems. I don't know about you, but I find writing all of those x's confusing. And as our systems get bigger and bigger in higher dimensions, it gets even more confusing. So we need a cute, compact form to help us simplify this solving. And to do that, we introduce matrix notation. So this is providing us with an equivalent way to solve a linear system of equations using a compact rectangular array called a matrix. So here we go. An M by N matrix A is defined as follows. So here is our rectangular array. And we want to think about the entries here. So the entries in a matrix are just the coefficients of your linear system. So our first entry is going to be A sub 1, 1. So this is the entry in the first row, first column. We then have A sub 1, 2. So that's the entry in the first row, second column. And we continue with this all the way until you get to the last entry. So this is the entry in the first row, nth column. And this goes down as well. So the second position here is the entry in the second row, first column. We'd have the entry in the second row, second column, and this continues merrily along all the way to the entry in the second row, nth column. Now, while they move across horizontally, they also move down vertically. So moving down column 1, we end up at the entry in the mth row, first column. We would then have the entry in the mth row, second column, and we continue all the way until you get to the very last entry, A sub mn. And so this represents the entry in the mth row, nth column. So even in just defining this, we can see that this M by N defines the size of your matrix. So the size of matrix A is defined as M by N. And this is where M is equal to the number of rows. So the number of rows are equivalent to the number of equations in the linear system. And we say that N is equal to the number of columns. And the number of columns is equivalent to the number of variables in an equation. So if we look back up at our matrix, we can see the correlation to the variables. So if we're thinking here about column number 1, this is associated with variable x sub 1. If we think about column number 2, this is associated with the variable x sub 2. And we continue all the way to get to your very last column here. And this last column is associated with the variable x sub n. So in thinking about it like this, we realize that the value of n dictates the dimension that the solution vector is going to be in. So we think back to the previous examples, this lets us know that that solution we're looking for, vector x, is going to be in Rn, or in n-dimensional space. So this is the dimension of your solution vector. So the dimension of our solution vector. So again, when we think about each of these columns associated with their variables, we realize that the entries of the matrix, all of these A values, are simply the coefficients of the variables. So we can make a little love note here to ourselves that all of the entries in our matrix, all of the entries, and we'll shorthand this and say A sub mn, are the coefficients of the variables. And so last but not least here, let's go ahead and specifically think about how we can define this last entry here, a sub mn. So we would denote this a sub mn, and what this is the mnth entry. It's a little bit of a tongue twister. And so this is the entry of the matrix in the nth row and nth column. So converting a linear system to its equivalent matrix notation is going to substantially simplify our computation. So to get us started, let's go ahead and begin by simply converting a given system to its matrix form. So here we go. Now, I want you to note that there are two types of matrices, and we're going to look at them both here. So let's begin by simply considering this beautiful linear system. So the first type of matrix is called the coefficient matrix. And the coefficient matrix simply has to do with the linear system on the left-hand side. So we're just thinking about the left-hand side of the equals sign. So how are we going to convert this linear system to its matrix form? Well, looking at this system, we see that we have 1, 2, 3 equations. So that's 3 rows. And we have 1, 2, 3 variables. So that's 3 columns. So the equivalent coefficient matrix is going to be a 3 by 3 matrix. And our first row will be 1, 2, 3. The second row will be -5, 6, -7. And the last row is going to be 0, 9, -17. So this is the coefficient matrix, where we're just thinking about the left-hand side of that equal sign. And we can see here that we have 3 rows and 3 columns, so that we can say that our coefficient matrix is a 3 by 3 matrix. All right, so in addition to the coefficient matrix, we have this second type of matrix called an augmented matrix. And now an augmented matrix incorporates both sides of the linear system of equations. So it's going to have your coefficient matrix, but in addition to that, we're also going to have a column for the terms on the right-hand side of that equal symbol. So here we go. Let's convert this to the augmented matrix. So we'll have that same coefficient matrix. We'll have 1, 2, 3. We have -5, 6, -7. And then we have 0, 9, -17. And then where the equal sign is, we'll draw a dotted line. So that is indicating to us that this is augmented. And then we have a column for the constant terms, -4, 8, 0. So these are the two types of matrices that we'll be working with, our coefficient matrix and the augmented matrix. And the last little note that I want to give to you before we go ahead and start looking at examples is that solving an augmented matrix or a coefficient matrix uses the same 3 basic operations that we saw with linear equations. So we can say that the same 3 basic row reduction operations are used to solve matrices, or to solve a system in matrix notation. So we're still going to use replacement. We're still going to use interchanging. And we're still going to use scaling. with the same exact format as we did before. So let's go ahead and take a look.